Hi, folks. So sorry that I couldn't be here in person today, but had a pressing PhD defense that had to be rescheduled into a time that overlapped with this class. And so that's why we are delivering this lecture asynchronously today, but otherwise it's going to run as if we were in class. And so I'm still going to stop for attendance slides. There'll be opportunities to ask questions in the anonymous question answering. And of course, you can follow up with me or the TA later. So today we are going to be talking about kind of our last foray into the advanced features of Insight Maker and Vensim for making your simulations more realistic. After this lecture, we're going to be looking into more of case studies and actually the fundamental modeling aspects of how do you build these stock and flow diagrams here. So this is really what are the last set of concrete tools that we can use inside Vensim and Insight Maker to make these stock and flow diagrams work. So last time we were talking about sliders and lookup tables and converters and units. And so of those three topics, units, sliders, and lookup tables and converters, it tends to be that lookup tables are very often a difficult concept. And so normally I would ask for questions here so that we can make sure everyone's on board with lookup tables. If you're having trouble with lookup tables, please let me know. Feel free to submit a question down here using the bit.ly 212 questions link or this QR code, or just post something to the discussions or to Slack or send me an email if you're having trouble understanding lookup tables, because lookup tables will be important and they will be a part of question 1 along with units and sliders of the assignment, the homework assignment E2. Now, the other half of that homework assignment will be about delays. And that's what we talk about here today. So delays, in our causal loop diagram, we've talked about in systems like these, then not only do we have to reflect the fact that there is a causal connection between some variables and another. So when I am hungry, I then eat more. So the amount of hunger I have has a positive influence on how much I eat. And we know that if I eat more, then that will have a negative influence on my hunger. And that's what creates this balancing feedback loop here. But although my hunger almost immediately makes me want to eat, as I eat, I don't immediately relieve my hunger. So there is a delay in this link back here. And that delay can generate all sorts of interesting consequences. So this is a big reason why you might overeat. You might overeat to say, you know what, I think I'm still hungry, when in reality, you have enough food to satiate your hunger, but there is a delay in the point where the food enters your system to the point where you actually experience relief to the hunger. And because of that delay, you can then overshoot how much food you need to eat to relieve your hunger and overeat. So that's the big reason why we really need to formally model these delays. Now, we in causal loop diagrams have put these delays in, but we haven't really talked about where we put them in the stock and flow diagrams, which is really where the dynamics come into play. So that's really important for us to do. So that's what we're going to talk about here today. So in order for us to talk about the concrete types of delays that we're going to put into Vensim and Insight Maker, we need to sort of separate out the different types of delays that we could get here. And so there are 2 types of delays that we focus on in this lecture and in this class. And one of them will be what we call fixed delays, which I'll talk about in a slide, and then smoothing delays, which I'll talk about in the bottom half of this lecture. So let's get into that. So fixed delays. So if we think about this food example, then if food enters the mouth at a particular point, then it travels down the esophagus at relatively constant speed and then hits the stomach. So here we're saying that there is a fixed delay from the point at which food enters the mouth and then reaches the stomach. So it takes a fixed amount of time for the food to go from the mouth to the stomach. And that's what we mean by a fixed delay. is that this is a delay that you know that it generally takes, I don't know, 3 seconds for food to get from the mouth to the stomach. And so in some ways that's an easier kind of delay to worry about, regardless of what type of food or how big the food is or anything like that. If you get a certain amount of food, that certain amount of food will hit the stomach in its full form after a fixed time period. So how do we implement these fixed delays? Well, let's look at Vensim as an example of this. So if we were to go into Vensim, we could draw a little diagram like this one. So I'm going to start simple, so I won't show you stocks and flows just yet. We're just going to focus on some simple variables before we actually involve the stocks and flows in this. And so we learned last time about shadow variables like time here. So you can create you can go in and create a shadow variable, and maybe I'll bring up Vensim so that we can see that. So if I bring up my Vensim here, then over here, I can create and let me maybe make my font a little bit bigger so that when I start placing things on here, it'll be readable. So if I go up into Vensim and I click on shadow variable and click on some spot here, it then says, what do you want to add? Well, I haven't created any other variables, but time is available to me. So I can bring that up there. So there's time, and then I can create other variables. And so I can say that I want a variable that is called ingestion rate. And I can create a variable that is called rate into stomach. And in my slides, I went and put a circle around these. I'm not going to bother with that here, but so we'll just kind of go back and forth here, but I'm just kind of mimicking what's going on in the slides. Okay, so I am going to say that time will be something that is used inside ingestion rate, and ingestion rate will be causally related to rate in the stomach. And so what I'm drawing here is that I am going to ingest food at a particular time, and that pattern of ingestion is going to be mimicked into the stomach at some fixed time later. That's what we're trying to simulate here. And so what I'm going to do here is what I'm showing here on the slide, is that if I were to go into this ingestion rate variable, I am going to set it up as an auxiliary here, and that auxiliary is going to have a lookup table. So we've learned about this all last time, and its input is going to be our time shadow variable. And what I'm going to do is in the lookup table, I am going to draw a pulse here, which represents food entering the system at a particular time. So in this particular lookup table, the input, again, is time. The output here, you can see it says 0, 0, 5, 5, 0, 0. Well, that's these points here. So the output, that's the y-axis, is 0, 0, and then it jumps up to 5, and then it stays at 5, and then it jumps down to 0. And so, and if I look at the times that correspond to that, it's at time 0, and then at time 5 is the first jump. At time 6 is the jump back down. And then at time 15, that's when I end the simulation here. And so this is a 1 second pulse of food into the mouth. The ingestion rate jumps up to 5 at time 5, and it stays 5 until time 6. And so if I wanted to build that inside Vensim, I can go into my equations here. So I can go into equations, I can click on ingestion rate, and it brings this over here. And I said that I'm going to configure this as an auxiliary. I'm going to then, under the subtype, I'm going to say with lookup. And then for the input for the with lookup, I'm going to make my time shadow variable. And then if I click on as graph, then I can say that I want my input go from 0 to 15, because I'm going to simulate 15 seconds here. And my output, I don't really care about as long as it's big enough. So I'm going to leave it from 0 to 10. And then I'm going to then say that I want at time 0, I want the ingestion rate to be 0. But then at time 5, I want the ingestion rate to start at 0, but then an instant later, so also at time 5, it will then jump up to 5. And by doing that, that gives me this edge here. this step up here. And then at time 6, it's going to stay at 5. So see, it gives me this top thing here. But then I'm going to jump back down at time 6, sort of an instant after that, back down to 0. So let's get those in the right order. And then at time 15, it'll still be 0. So I was able to create this little pulse. And this pulse starts at time 5, and it jumps up to 5. It stays at 5 until time 6, and then immediately after time 6, it goes back down to 0. So this is simulating that as the simulation is going on, at time 5, somebody puts a carrot or a hamburger or whatever into their mouth, and that causes the ingestion rate to jump up, but it's only in the mouth for a short period of time, and that's what we're simulating right here. Okay, so if I click OK, it populates the lookup table down here as expected. And that's good here. So that's not involving the delay yet. So let's go back to our slides. And so this is just showing us here that everything that we just did here. And if I were to simulate this, so I guess I can go and do that. So I'm going to go into my model settings, and I will bring those settings over here. I'm going to say that I'm going to simulate 15 seconds. Maybe I'll use a time step of 0.1, maybe 0.05. And then I'm going to use time here in seconds. And then I can't simulate this yet because I haven't put formulas into this rate into stomach. So when we get the formulas in there, I'll go ahead and simulate this. But if you were to cut to ahead, when this is a working simulation, then if we were to just monitor ingestion rate, then what we would see in this ingestion rate is exactly what we drew in the lookup table, is that this ingestion rate after the simulation will be 0 until time 5. It will jump up to 5. It'll stay there until time 6, and then it'll come down to 0 after time 6 all the way to time 15, which is when the simulation ends. Okay, so that's all that we're building here. No delays yet. That we're just using the shadow variable time and the lookup tables to create this ingestion rate that changes during the simulation. Okay, so where do we go from here? Well, this is where the delays come into play. So what this is showing us is if we go into the rate into stomach here, then what I can do is use this formula here where Vensim has this thing called delay fixed. And delay fixed basically says that its output, so by its output, that's the rate into stomach, is just going to be a delayed version of whatever you put in here as the first argument. And it will be delayed by whatever this time is here. And when you start the simulation, it won't have any initial information for what goes into here. It's kind of like if the simulation starts at time 0, we need to ask, well, what's the rate into the stomach? Well, we actually don't know what the rate into stomach is right at time 0. So we are going to assume that the rate into stomach starts at 0. And then, so for the first 5 seconds of the simulation, it's just going to be 0. And then after the 5th second, it will be the delayed version of whatever was in ingestion rate. So let's see what that looks like. I'll go back into Vensim, and I will bring my Vensim back over into, once I find my mouse again. In theory, I will bring my Vensim back into here. Okay, here we go. Okay, here we go. So if I go into rate into stomach, down here, it's got a bunch of functions that are already available for you to use. So you can manually type delay fixed, just like I did on those slides, or I can go down here in these functions and I can find, oh, look, delay fixed, it's right here, how convenient. When I click on that, it gives me a reminder of what the arguments are. So it says in here, well, I can highlight that and get rid of the in and instead put ingestion rate. For delay time, I'll put a 5. And for the initial version of the rate in the stomach, I'll put a 0, which just means that the initial rate in the stomach will be 0 until time 5. And after time 5, it'll just be a copy of whatever the ingestion rate was 5 seconds ago. And that's how we simulate this fixed delay. So then I've now got what I hope is a working simulation. So if I were to click simulate, then it then is telling me that my lookup is out of bounds. So let's deal with that. So what happened here? So I ran this simulation, and this error message is gigantic, and I don't know if it's going to, let me move it into another screen and see if I can make the error message smaller so that it fits within the share screen a little bit better. All right, now if I move this back, it says lookup out of bounds at 15, above ingestion rate, computing ingestion rate. And so if what this is telling me is if I go into my equations for ingestion rate, and then if I were to go into this as graph, it's saying that this is defined up through time 15, and it's complaining that at time 15, it's as if the simulation were running a little longer than it should have. So if I were to go into this, into my model settings, and change this, where model settings go, there they are. If I were to change my model settings to 14, then I think that will fix the problem here. So I think what happened here is I set the simulation to run for 15 seconds, but due to some numerical rounding errors, due to my time step here, that caused the simulation actually ran to time 15.00001 or something like that. It ran a little bit long. And my lookup table was only defined for time up through time 15. So in this point, I can say, all right, if I just define I'm going to stop the simulation at time 14 because that's plenty of time, then I should be okay because my lookup table is defined all the way to 15. So it should deal with any rounding error. So let's see if that actually worked. So now I'm going to hit my run, and it then ran okay, no errors whatsoever. So that was a way, I dealt with this particular error. So now if I go in and I then plot the ingestion rate and the rate in the stomach, I'm going to just hit graph here, and let's see what I get. So here they are. And the plots here, it might be hard to read these axes, but the blue line here is the ingestion rate. The red line here is the rate in the stomach. And as expected, the ingestion rate does what we thought it would, what we programmed it to do. From 0 to 5, there's nothing in the mouth. From 5 to 6, there's a carrot or a burger in the mouth. And then from 6 to the end of the simulation, the mouth is empty. Then from 0 to 10, there's nothing in the stomach. From 10 to 11, there's the rate into the stomach is 5. And then from 11 to 14, the rate into the stomach is back down to 0. So I hope you can see what happened here is that for the first 5 seconds of the simulation, the stomach was empty. And then after that first 5 seconds of the simulation, the stomach copied whatever was going on in the mouth. And so in the mouth was empty for 5 seconds and then was full for 1 second. So after the first 5 seconds of the simulation, we just copy that mouth signal and we're got 5 seconds of empty and then 1 second of some rate into the stomach. And then after that, just like the mouth falls off, the stomach falls off. So that's what the fixed delay does, is if you've got something going on in one part of the simulation, if you implement a delay fix somewhere, it's just going to copy whatever happened earlier in the simulation to a later point in the simulation at that particular variable. So that's what we did here. Ingestion rate was the input. Rate into stomach was the output. Rate into stomach was just a copy of whatever went on inside ingestion rate. So going back to the slides here, this is exactly what we simulated. So if I go back to the slides here, there's my delay fix that I implemented in the rate into stomach. And then if I go and simulate that, then as expected, the blue line is my input, that's what's in the mouth. And the red one, that's what's going into the stomach, is just a copy of the blue line shifted over by 5 seconds. Because it's just simulating the fixed delay, the 5 second delay down the esophagus. So stuff happens here, the exact same stuff happens in the stomach 5 seconds later. That's what we mean by a fixed delay. And that is implemented in Vensim with this little function, delay space fix, where the first variable is, which has to be provided via a link as an input, then how long you want the delay to be, and then what you want when you initially start the simulation, when there's no information available from the other variables to copy. So normally we just set this equal to 0. All right. And so like it's just saying this is a 5-second delay here. Okay, so how does this relate to our stock and flow diagrams? Well, this doesn't look like a stock and flow diagram. There's no stocks and there's no flows. So if we think about it, the stuff that's in the mouth is a stock, and the stuff that's in the stomach is also a stock. So the current amount of food in the mouth is a stock, and the rate into the mouth is a flow into the mouth, and the current amount of food in the stomach is a stock, and the rate into the stomach is the flow corresponding to it. So I'm just going to redraw this basically as a stock and flow diagram, where I see now that the flow going into the esophagus is just, so I said into the mouth, but we can also just say the esophagus is basically the stock. So the food in the esophagus, that is the thing that we're calling a stock. That is that kind of holds the memory of the system here. And we're saying that the food in the esophagus is initially empty, but it starts filling at the ingestion rate, and so that's what fills the esophagus up. But then after traveling through the esophagus, then the food leaves the esophagus and goes into the stomach. So the ingestion rate that we modeled on the previous slide is like an inflow into the esophagus. And the rate into the stomach is like an outflow from the esophagus and an inflow into the stomach. So that's all that we've drawn here. So we've basically just taken the two variables that we had in the previous slide. So if I go back to that, here's the two variables, and we turned them into flows. And we had to then put stocks in between those flows. So this ingestion rate, that's going to have the exact same formula as it did on the previous slide inside it. The rate into stomach is going to have the exact same formula in the slide, on the previous slide, right inside it. And then we just put stocks in between them to kind of catch the food as they come in and out of these flows. So as the ingestion rate dumps food in, it gets caught by the esophagus, and then it's held there, but then 5 seconds later, it's pulled out of the esophagus and put into the stomach, and the stomach catches it there. And that's where this model kind of comes from here. Okay. So if I were to redraw that in Vensim, which I guess I could go and do. I don't want to take too much time in doing this, but basically you could imagine me going into Vensim here and then drawing stocks, these levels. I could have this be the food in esophagus. Oh, that is not how you spell esophagus. And I've lost my mouse again. There we go. So let's see what I actually spelled. That was close. It's not quite right. Esophagus. And then I can draw my food and stomach. And I can make that a little bigger if I want. And then I could draw these rates. So here's the rate going into the esophagus, and that's my ingestion rate. And I am going to call this ingestion rate 2, just because I have the ingestion rate already on here. And that way it won't complain to me that I've got two things named the same thing. And then I'm going to draw this thing in here, and that means my rate into stomach 2. And then now I just connect time to this one, the same I did over here. Connect ingestion rate to rate into stomach, the same way I did before. And then I should be ready to put the formulas in. So my food into esophagus is just a stock that starts empty, so it's going to have an initial value of 0. My food into stomach is a stock that starts empty. It's 0. And then my ingestion rate here, then I am just going to go into the previous ingestion rate and copy this. So I'm going to go through here and say copy, and then I'll go down here. And if I wanted to, I could have redone that whole lookup table again, but I don't want to take the time to do that, which is why I'm just copying that in there. And then for rate into stomach, I can do the same thing where I'll just copy this formula and paste it into here. So exact same thing, but now I need to change this to ingestion rate 2 because that's the name of the variable going into it. See that? Okay. And then now I don't need these things anymore, so I can get rid of them, but I need the time still. So here, if I go and simulate this thing, I get no errors. That's always good. And then so now I can go through and I can plot all 4 of these things in a graph like I've got right here. And I'll go back to the PowerPoint slide in a second and you'll see the exact same graph, but I think it'll be a little clearer. But basically the green line here is the ingestion rate into the esophagus. The gray line here is the rate into the stomach, which is a rate also out of the esophagus. And the blue trapezoid looking thing here, that is the food in the esophagus. So you can see that at time 5, food gradually moves its way into the esophagus. And while it is moving down the esophagus, then there's a constant amount of food in the esophagus. That's what's being shown here. And then when it hits the stomach, it leaves the esophagus and goes into the stomach. And that's why you see a ramp that comes down here. And then the red line that you see here, that is the food into the stomach. And you can see the stomach is empty until time 10, where gradually food hits the bottom of the esophagus and starts entering the stomach. And then that goes up here. And there you go. So let's go back to the PowerPoint and we can see that that's exactly what we were expecting. There you go. So I just, there it is right there. And again, the 5-second delay. So that is how we implement these fixed delays in Insight Maker. Now all we need to do is to see how to do that. I'm sorry, in Vensim. Now all we need to do is to see how to do that inside Insight Maker as well. But before I do that, I just want to remind you that if you have any questions, then you can, again, hold on to them and ask me them later. Or if you'd like to, you can go to the bit.ly/212 questions or scan this QR code and you can post some questions there. And I will be sure to check into that and monitor those and then post answers to those questions to the discussion. So that's another way you can do that. All right. And I actually can, just for those of you watching this on Zoom, the Zoom replay, the recorded one, I can go ahead and put that URL right into the chat. So if you look at the chat on the Zoom, you can see that URL there. Okay, so let's go back to seeing how this looks in Insight Maker. So in Insight Maker, it's exactly the same type of process, just a slightly different syntax, slightly different graphical syntax. The idea here is we go into Insight Maker and we then create a lookup table, but we create lookup tables in a slightly different way. So let's, which we remember from last time. So I can create new insight. Maybe, all right, here we go. Clear that. Then I can go up here and I can say add converter, and I can call this converter ingestion rate. And I am also going to add a variable, which I can call rate into stomach. And in my ingestion rate, the input here I set as time. So I don't need to create shadow variables. It just has that as an option. if I were to drag anything else to this to connect to it, then those options would also show up here, but by default, it's always time. And then, and so at this point, I just need to create my lookup table inside here as I had done before. And so I can click on the little equal sign here, and that brings me to a lookup table editor. And I can set, what I'm going to do here is I'm going to set the interpolation, which is over here, not to linear. I'm going to set it to none. And that is going to make it easier for me to put in this lookup table. So now under that basically allows me not, whereas in Vensim, I had to sort of whenever I had sharp changes, I'd have 2 times, one time at the bottom of the change, one time at the top of the change. In when I have the lookup table in Insight Maker set to none, then I don't need to do that twice. And so if I want food to enter the system at time 5, and I want food to then at time 6 to go back down to 0, then and then it's linearly interpolating. So let me see why here. All right, there, that's better. I don't know why there was a delay there, but because I've set this to interpolation none, then it automatically gives me the sharp points here where, so I'll say at time 15, we're going to be down at 0 still. So, oops, time 6. All right, yeah, there I got it. So then you see here, I only have to define 4 points. At time 0, it'll be 0. At time 5, it jumps up to 5. Because this is the so-called none interpolation, as no interpolation, it knows that it's just going to hold the previous value until it's told a next value. And then it goes up here. And then it holds that until the next value, which at time 6 goes back down to 0. So it'll go back down to 0. And then it holds onto that until time 15. So same thing we did in Vensim. I'm going to go into my model settings. I'm going to set the simulation length to 14 seconds as before. And then I'm going to draw an arrow. So from the ingestion rate here into the rate in the stomach. So I click on the little links up here, and then that allows me to then grab one of these and drag it to the other one, and it's pointed in the right direction. If it wasn't, I'd have to click this thing to flip it around. And then that will allow me, if I go into my rate in the stomach here, now I can implement a delay. So we'll get right back to that in just a second, but I just want to catch us up in the PowerPoint for those following along in those slides. We just went into ingestion rate. We set the interpolation to none. We set the input source to time. And we then created this cool little function here, which goes from 0 to, this goes to 14, but I could have done 15. I think I did 15. And this one, in this example, I went to 14. And I think I had, in my example, I mimicked Vensim in the example that I did for you in the web browser. But in this example, you can see I use different times. So it goes from 0 to 1 and then 1 to 2. So at times of 1, it jumps up to 1, then it jumps back down to 2, and it holds that until 14. And if I were to simulate this thing, then and plot the ingestion rate, then it would look exactly like my lookup table. Okay, now as kind of an advanced thing here, what I could have also done inside Insight Maker is, instead of using a lookup table, I could have brought a variable in here. And in this variable here, there's actually already a function inside Insight Maker called Pulse that will generate exactly what I want, exactly the same pulse that I want to generate here. So in this case, if I go back to the web browser here, I get my mouse back, here we go. So if I were to bring in a different variable here, and in this variable here, if I go into its edit here, if you notice, there's a bunch of cool groups of functions here on the right. And I think one of these functions is called time. One of these groups is called, oh no, it's not time functions I'm looking for, it's general functions. If I look under general functions, I can find under here a pulse, which reminds me that there's time, height, width, and repeat. And so the idea here is I can tell it at what time do I want a pulse to be generated. And if for the example I do in the slides, it's at time 1. For my example, it's at time 5. I want that to go up to a particular point. In the example in the slides, it goes up to 1. In my example, it goes up to 5. I want it to be to last for this long. That's what we mean by width. And I can actually then have it repeat the pulse over and over and over again, like a pulse train. But I'm going to set that equal to 0 here so that I don't want it to repeat. Or I don't want it to repeat, and I only want it to happen once. That's one way to say that. So I think it'll actually, I don't know if it's going to let me leave those words in. I think it actually does let me leave that in there, but you can also get rid of those. So it just says 5510. All right, so those are 2 ways to do the same thing. So I can just leave this up here as ingestion rate 2. And it would, do the same thing. So if I were to plot this stuff, let me see if it'll let me simulate. And I think it's complaining about the fact that I left the width in there. So let's do that. Get rid of those. And if I were to simulate that, there's an equation error that must be corrected. Oh, I didn't even notice there's a little 0 out here I accidentally placed. All right, so now if I try to simulate that, then I end up seeing that both of these, well, let me go up to my settings and change my simulation time step to 0.05. Now, if I simulate that, then what I can see is that I'll go to full speed here, that at time 5, so let's turn on a legend here. So I'm going to go to configure, go down here to chart settings, and there is a legend position. Let's set it to automatic. And it's plotting everything right now. So I'm going to turn off the rate into stomach because we haven't gotten there yet. And I've got ingestion rate in green and ingestion rate 2 in red. If I turn off the green one, this is ingestion rate 2, and you can see, as expected, at time 5, it jumps up to 5, it hangs on there for 1 second, and it jumps back down to 0 at time 6, and hangs on to there until time 14. If I turn on the other ingestion rate, which does it the lookup table way, it's the exact same thing. So that's all that we're saying back in the slides here, is that you can do this with a lookup table, or use this handy dandy function called pulse that'll do that for you. And that's all we're saying here. Get rid of the words width and repeat that show up there. Well, I don't know. I really think it's okay with those there. And the problem I had was there was a 0. But in the slides here, I've gotten rid of them. So that's kind of an easy way to do it. So this is, like I said, this is exactly the same as the lookup table. All right, but in Vensim, we also have a pulse function that we could have used. It's called Pulsar pulse train. And so likewise, if you don't like using the shadow variable in Vensim, you can instead get rid of the shadow variable and just create a variable or a flow that uses pulse or pulse train. There are very similar functions that are defined already in Vensim. That's all I'm kind of saying here. But the real reason we're here is to talk about the fixed delays in Insight Maker. So if we go into the rate into stomach variable inside Insight Maker, then we'll find that under historical functions, this grouping here, there are a bunch of delays, and the delay function here is what Insight Maker uses for the fixed delay. So, and it does have an initial condition, just like Vensim's delay fixed, but you can leave it out. And if you leave it out, then it matches the initial variable that you're trying to delay instead. So it's kind of like if your initial variable delay was, if your initial ingestion rate was 0, then that means your initial rate in the stomach is also going to be equal to 0. by default here. If you force something by 0, then you're saying that for the first 5 seconds of the simulation, I want this thing to be equal to 0. And then after that 5 seconds, I want it to be whatever I put in here. So just to show you where that is, I go into my web browser, I go into a little equal sign here. I can then say, I want this to be historical functions, delay, and then this thing that says primitive here, I then put the ingestion rate that's linked into there as my reference, the input here. I want the delay length to be 5. And the default value I'm going to make equal to 0. And so there we have it. So now I will get rid of this guy, this ingestion rate here. I'm just going to right click on it and say delete. And I'm going to simulate what remains here. And we get exactly what we saw in Vensim, where at time 5, it jumped up till 5 and then went down to 6. That's the ingestion rate. And then 5 seconds later, we see that the rate in the stomach jumps up to 5, goes over, and then comes back down. All right. So that's all we're saying here as well, that we've got a 5-second delay. So we can do this just the same. Now, going to stocks and flows, same story. I'm not going to manually do this inside the web browser, but you could imagine a very, very similar story as to what we did in Vensim. You could bring in a stock, bring in another stock. Those become the actual food in the esophagus at any instant of time, the actual food in the stomach at any instant of time. And then you can draw flows into those. The rate in the stomach is simultaneously an outflow from the esophagus and an inflow into the stomach. And all we're saying here is that the rate into the stomach is a delayed version of the rate into the esophagus. And that is how we simulate a transport delay, a delay down the esophagus in transport there. And so if we were to simulate that, we get exactly the same output that we get inside Vensim, is this ingestion rate pulse, which is followed then 5 seconds later by an identical pulse of rate into the stomach. And when you then think about what that actually means for the food in the esophagus and in the stomach, then in between times 5 and 11, there's food that ramps up into the esophagus, stays in the esophagus as it's transported down the esophagus, and then comes down to 0 as it exits the esophagus. And as it's exiting the esophagus, it's entering the stomach, which means that after that time point, it stays into the stomach. So that's an example of simulating fixed delays in the esophagus. There are a bunch of other ways you do fixed delays, like or reasons why you might want to do fixed delays, like schooling behavior. So if we talk about tight schools of fishes, then in those cases, we've got a bolus of fish, so a ball of fish that is moving together. And so when the fish are here and they're moving in this direction, then a few seconds later, that entire ball will be the exact same shape, but just shifted over. So that is an example of simulating a transport delay, the same way you're simulating a delay down the esophagus. So that's what I mean by schooling behavior, that type of thing. Similarly, students moving through a school system act a lot like that. So you have students in first grade, those same students generally are going to be the students you see in second grade. So if you wanted to model the population dynamics going from one grade to another, then all you really need to know is what the population looked like in kindergarten. And then you're going to know what the population is going to look like a year later in first grade and a year later in second grade and so on. So the first grade through 12th grade dynamics are just copies of whatever interesting things happened in kindergarten, that a number of time steps backward. So that's what we were talking about when we talk about an age structure. Cohorts at one age will be the same cohort at another age later. So we can talk about you have a cohort in kindergarten that are a certain age. When they go into first grade, it's the same cohort and they're all that age later. So it just so happens that this feels like a school of fish moving through here. And it would be really nice if the etymology of school matched the etymology of schooling behavior in fish. It turns out they don't. It's just a nice coincidence. It has to do with shoaling in fish, and it's a different word in the schools. But it is easy to keep in mind that if you want to simulate cohorts as they move through a system, that is identical to simulating fish as they move through a physical system. So the cohort itself isn't changing, but so once you know what it looked like at one time, you're going to know what it's going to look like at future times in other parts of the system, because it's just going to be copies of what it looked like at previous times. That's an example of where we use fixed delays. And then, just generically, transit delays in traffic systems, material flow, again, getting materials from one point to another. These are all fixed delays. All right, so that's the first type of delay that we had to cover today. If there's questions about that, again, I encourage you to, and feel free to take a pause here, to go ahead and, ask questions in the questions link that I posted on the chat earlier, or click on this QR or scan this QR code in, post questions there, send me a note, post something on the discussion boards, etc. All right, this is a great time for us to then do an attendance exercise to give you some credit for sitting through all this so far. I will put this URL in the chat in case you're watching this in the Zoom version of this broadcast. And the question that I am going to ask here is, give an example of a fixed delay. Just give me an example of something that you view as a fixed delay. All right, so moving on. If we are thinking about the hunger, satiation feedback loop, then are fixed delays the only things that we need to worry about up here? Well, it turns out they're probably not all of the delays you have to worry about, but it's probably not the most important delay. Because if you really think about it, the time it takes to get food from your mouth to your stomach is really not the thing that is slowing down your ability to say, okay, I've had enough. It's how long it takes to process food in the stomach. So that's the other type of delay that we need to focus on, the so-called smoothed or smoothing or averaging delay. And so this is the idea of how long it takes food to get from your stomach into your bloodstream. So here, the blue line here is like food that has reached your stomach. Your stomach has suddenly got food in it. Now, the food in your stomach, some of it is going to immediately be absorbed into the lining of your stomach and reach the bloodstream, the nutrients into that, where there's a bunch of it is just going to sit there and wait. And so even though, that food might have taken you a few seconds to eat and swallow, it might stay in your stomach for hours, or an hour or something like that. So this idea that you start out with your cohort or whatever, but then you have to spread it out over time, that is an example of a smoothing or averaging delay. And so the idea here is that the input can change instantaneously. So the amount of food in the stomach, it can change instantaneously, but the output, the nutrients going into the bloodstream, well, that is much more sluggish. You can end up getting nutrients entering the bloodstream for a very long period of time, even apparently after food has exited the stomach, because it's tied up in all of the absorption processes in the lining of the stomach. So this is also known as exponential damping or exponential decay. And this should remind you of like the toilet flow example here, where you have a sudden, the toilet suddenly becomes empty, but the water that enters the toilet enters it more sluggishly, so that you do have some water that enters the toilet immediately, but the water that ends up filling the toilet to its set point ends up being water that takes a very long amount of time to arrive. And so we view the filling behavior over time of the toilet as a smoothed out version of the actual flush of the toilet. So the input of the toilet is like flushing the handle. That's like an instantaneous disturbance of the system. And there is a response to that, but that response is drawn out over time. It's spread out over time. It's smoothed out. And that is the different type of delay that we're talking about here. And so when we think about that, we talk about there's an input here and a delay. But the delay here isn't a fixed delay. It is a characterization of how sluggish the system is. In other words, it is a characterization of how steep this red curve is. So how close does this red curve approximate this blue curve? That's really what we mean here by the delay. So in the stomach case, the food entering the stomach is the input, but the digestive efficiency, how quickly you can absorb that food into the bloodstream, that is like the smoothing delay here. Now, this in itself is like a dynamic process. And so that in other words, it's like we can't, it's not as simple as just saying that the food in the stomach is a delayed version of the food in the esophagus or food in the mouth. We actually have to sort of say the food going into the bloodstream is itself another stock. So it's almost like the food in the stomach is one stock and the food going into the bloodstream is another stock. And the way the flow going into the bloodstream stock is going to have sort of a more complex pattern to it. So let's zoom in on that and see what that looks like. So we build smoothing delays. I'll end up showing you there's a module where this is done for you in both Vensim and Insight Maker, but we can do it manually, and we would do it manually with something that looks like this, where the bloodstream is kind of like the average here, and the input is kind of like the food into the stomach. And we can build a little stock and flow here, where we're saying here that even though the food into the stomach arrived instantaneously, we initially assume that the nutrients in the bloodstream are 0. And based on the difference between the food in the stomach and the nutrients in the bloodstream, then there ends up being a flow of nutrients into the bloodstream, increasing the amount of nutrients in the bloodstream. But that is going to be slowed down by this delay. And so this here is the formula that goes into this flow equation here. Average is the output of, and the input is the food that goes into the stomach. And there is a rough relationship between how the input changes and the average changes, but because there's this flow that's in between them, then the output, which we're calling average here, which is like the nutrients going to the bloodstream, is like a smoothed out version of the input. The input changes instantaneously, the average is stretched out. And like I said, this is identical to what you've already seen in the toilet flow example. So in that case, remember that we had a target minus the level divided by a delay. In your homework example, we just assumed the delay was 1 second, and so this denominator wasn't there. But then afterwards, we said, well, if we were simulating a slower toilet, we would use a longer delay here so that the flow rate going into the toilet would be target minus level divided by a bigger number. And so that bigger number was this delay that we're talking about here. And so we've already kind of seen this already before. The input is the target height of the toilet, and the output is the water level. Okay, so that's the basic structure of what goes on behind a smoothing delay, and there is an alternative way that we can draw it. And so that alternative way that we can draw it is, instead of drawing an input minus an average showing up as the net inflow, we can show that we can say the input divided by the delay is like the inflow, and the average divided by the delay is like the outflow. And this makes it look almost like a birth-death type of process, where this is like, if this was the number of bacteria in a system, this is almost like, the deaths, where the delay here is the average time until when they die. And then the input here is like a birth process, where the input is like, bacteria that are being somehow injected into the system with some rate limiter, which happens to be the same delay, which is kind of the average lifetime here. So all we're doing here is we're just breaking up this here so that we put the input and average as separate flows. And by doing that, it just allows us to get more insight into why this is often called averaging. Because if we think of this version here, which is identical to this version, but we've broken up the inflows and outflows, then we can imagine writing the formulas that are being implemented behind the scenes, like this formula here, where we've got the average at any time is the average of the previous time step, and then minus, that's the outflow, dt, which is the time step, times the formula there, which is the average of the previous time step divided by delay. And then the inflow plus here is going to be that time step plus whatever the input was divided by that delay. So this is just writing out what is going on in Vensim as it kind of implements the spreadsheet behind the scenes. And so that allows us to sort of think about, well, why do you call this averaging? Well, if I look at this expression here, then I can do some rearrangement. And that rearrangement here just says that the average at the next time step is the average at the previous time step times this 1 minus dt over delay plus dt over delay times the input here. So that's just algebraically rearranging this expression up here. And by rewriting it that way, then it's pretty clear that the average at any time step is just the weighted average of the previous average value plus some component from the input. So in the no delay case, where delay is equal to the time step, which basically means that in one time step, whatever happened on the input will show up on the output, then basically this term goes away because dt is going to be equal to delay, or rather delay is equal to dt. So this becomes a 1 and this becomes 1 minus 1, and this whole term drops off. It just becomes a 0. And so in that case, then this term here just becomes a 1. And so the average, which is the output here, will be equal to exactly what the input was at the previous time step. If we instead make the delay very large, so we could call it practically infinite, then this dt over delay is going to be equal to 0. So this thing in parentheses is going to be equal to 1. And this dt over delay is going to be equal to 0. So that's going to kill this whole term. And so that will mean that average will just be equal to the previous version and will have no impact from the input. So we call it averaging because this formula ends up showing that the output, which is like the nutrients entering the bloodstream, is a weighted average, kind of like our stage 2 exam. Your midterm score was a weighted average of your stage 1 score and your stage 2 scores, 80% your stage 1 and 20% your stage 2. Well, that's kind of like this here. The current value of the nutrients into the bloodstream is the previous value of the nutrients into the bloodstream weighted by some fraction, plus whatever food is currently in the stomach weighted by some fraction. And those two things add together, and then that's how you get the nutrients going into the bloodstream. And you can also call this an averaging delay because delay is actually the average delay of any small fraction of food in the stomach. So if you eat a tiny little, if you eat a bunch of kernels of corn, then you could sort of say, how quickly did each kernel of corn get absorbed into the bloodstream? Some of those kernels of corn will get absorbed into the bloodstream very quickly. Others of them will be sitting around for a very long amount of time. Over the entire population of all the corn kernels sitting there in the stomach, there's going to be an average amount of time waiting in the stomach to go into the bloodstream. And that is also another interpretation of what this delay value is right here. All right. So that delay value can also be called the mean lifetime, which we'll find out, I'll remind you in a second, is the time constant, which we have introduced in the past. All right, so smoothing and averaging delays. So this idea here is that, and so maybe I can, so we went through these formulas here. So before we kind of talk high level, then I'll throw up the question slide. Again, just for those of you who want to stop, take a breath, maybe post a question. I can post the question slide URL as well for those of you who'd like to post a question. just generally about, what the heck's going on with these formulas and things. I don't want to get too caught up in the formulas because, again, Vensim and Insight Maker both provide a module, which I'm about to show you, that takes care of implementing these formulas behind the scenes for you. What I want you to try to keep in mind is an interpretation of what the delay parameter means in terms of smoothing delays. In fixed delays, it's easy. It's exactly the amount of time it takes to get from point A to point B, fixed delay. In a smoothing delay, that delay parameter is the average amount of time any small unit of a group that enters the system takes to exit the system, or to exit that component of the system. So in a fixed delay, everybody takes the exact same amount of time to get through that part of the system. In a smoothing delay, some parts will end up getting through quicker than others, and the delay is the average amount of time it takes for them to get for the population to get through. All right, so let's go back to this smoothing delay here. All right, so what, again, trying to get our comfort on our interpretations of what smoothing delays are, is that smoothing delays occur because systems have inertia. Systems cannot change instantaneously. And this is exactly what Newton was saying when he had Newton's second law. Newton's second law basically says that a net force applied to an object produces a proportional acceleration in the direction of that force, and an object's mass represents the relationship between the change in the force and the subsequent change in velocity. In other words, if you push on an object, if that object's heavy, then a small force that's being pushed on it is not going to accelerate the object very quickly. But if you push on a light object, then you're going to see a very fast change in that object's velocity. So the mass of an object is how sluggish the object is to change. If you view the force as an input and the acceleration as an output, then this mass here represents that large forces may produce small changes in acceleration if the objects have large mass. And that is going to create a large smoothing delay or averaging delay. And so just to kind of make a point of that, F equals ma, that's Newton's second law. If you remember, acceleration is just the rate of change in velocity over time. So this is just another way to write F equals ma. So this right here looks like the equation of a flow. So it would be nice if I can then write it like a flow. So this is like if velocity was a stock, this would be the flow going into velocity. And that, if that F equals ma that comes from Newton's second law, that's just going to be F divided by m. This is me just rearranging F equals ma. And this is just showing you that the flow going into the velocity stock is going to be a scaled down version of the force being applied on the system. And it is scaled by the mass. If the object has a very large mass, then the same force is not going to produce a very large or very fast change in the object's velocity. And that's all that's being represented here. So the change in velocity is just the force of the change scaled down by the mass of the object. And that more generally goes back to a change in any variable in our system is the force applied to that change divided by our variable's inertia. And so that term inertia has to do with how sluggish systems are. In the case of pushing on massive objects, an object's inertia is equivalent to the object's mass. But in the case of our systems, the inertia might come from other things. And so we won't characterize them by mass, but we'll characterize them by time, which will be how quickly things get, or how sluggish things are, how quickly our applied forces actually lead to a realized change in the system. So a system's inertia or mass causes desired changes, this is the green line, to be smoothed out over time by a certain amount, which we can characterize by inertia. And the delay length used in our simulation is tuned to match the effect of a system's inertia. So we choose the delay length so that we get the proper input-output balance between our requested change and how long it takes for the actual change to happen. And so in the real world, mass is a physical measure of inertia. In our simulations, we will simulate inertia with the effect of inertia on time, on when we want to change, how quickly does that change actually happen. So other examples of inertia, we talked about mass, heat capacity. So when you heat up water, even though you're immediately heating up the pan that your water's in, the water temperature doesn't immediately change. And that's because the water has heat capacity. If you have a very large bucket and you want to fill that bucket, even though you start putting water into the bucket, the height of the water doesn't change very much, because if it has a very large diameter, then you need to put a lot of water in order to start raising the water level very high. So the width of a bucket represents the inertia of the system, its resistance to change in height. We can also get more abstract. If we're modeling social systems, there could be groups of people that do not change their opinion very readily. And that might be represented by a stubbornness parameter. All of these things we might simulate by a time delay in terms of one of these smoothing delays. So you try to, you put you advertise a recycling program, and you want to simulate how quickly it'll be until people start doing the recycling. Well, you may need to simulate one of these smoothing delays where the stubbornness of your audience is going to be the difference between the step when your ad started running and then how quickly people started adopting the new behavior of recycling. And there are plenty of other examples of that. And a change in a system variable, when we think about stock and flow, that's just the flow into a stock. The force of a change, that's the desired change in the stock. And then the system's inertia is just a parameter which scales down the desired change when it translates into the actual change in the flow. And that's, again, just F equals ma. All right, so this is me just hitting over the head with these interpretations, this abstract interpretations of what these smoothing delays are. Let me be a little more concrete, because I think that might help here. If we're trying to model a city intersection, then we really have a tale of two delays here. The idea here is that there are cars that are at one intersection, there are cars in between the two intersections, and there are cars at the other intersection. If we think about cars that are waiting at an intersection, and then we think about how the cars then spread out to then travel in the period between the intersections, then we can think that there are some cars that immediately get into the road segment between the intersections, and other cars have to sit there and wait for those cars to get out of their way. So that is an example of a smoothing delay. So we have a group of cars clustered together in the intersection waiting for the light to turn green. It turns green and they spread out, and some cars get into there faster and some slower, and we can model the average time it takes for a car to get out of the intersection into the road segment as this parameter here, which represents this smoothing delay. Now, if we think about how long it takes for them to go through the road segment, then if we're imagining all cars are traveling at roughly the same speed, once they spread out into the road segment, they're pretty much going to stay in that position over the whole road segment. Now it's like our esophagus. So we can simulate the delay down the road segment as a fixed delay. So imagining the cars arriving at intersection B, well, the same cars that entered the road segment are going to enter intersection B in the same pattern they entered the road segment, because that transportation delay is just a fixed delay. So those are examples where if we were modeling cars moving through a city using system dynamics modeling, we would need to use smoothing delays when we model the stoplights and fixed delays when we model cars moving from one intersection to another across road segments. Okay. So again, if you have questions about that, feel free to post those. Otherwise, let's have one more attendance question. So I can put the URL in the chat for those of you watching the archived version on Zoom. And the question that I will ask here is give an example of a smoothing delay, or give an example of a, so I'll just say, give an example of a smoothing delay. So just give me one of the example systems or another system you can think about that would be modeled by a smoothing delay if you're modeling that system. All right, so let's get through some of the other stuff, kind of quickly here. So if you want to build these delays, you could build these complicated stock and flow structures every time you want to build a smoothing delay. Fortunately, Vensim and Insight Maker have already done this for you. And so if you go into wherever you want your smoothing delay to be, you go into the equations, and then inside Vensim, you scroll down into the functions here, and you will find a smooth. And that smooth here is has an input and a delay. The input is the variable that you're, I don't want to say copying from, but that is the driving variable. The delay is this average delay that's going to create this smoothing. And that's it right there. So you can find that again under this. It's the same sort of thing. You draw an input going into it. You might draw in the delay going into it. You find smooth. Whatever variable you've brought in as the input goes under input. Whatever delay you want, using this average delay kind of interpretation, or this time constant interpretation, that goes as the second parameter. So here it is more concretely. I've got a 2.5 second smoothing delay for my input here. So if I were to simulate such a thing, if my input looked like this square wave, this blue square wave that changes instantaneously, then my output that would come out of Vensim would end up looking like this red curve. And that is kind of meant to mimic this nutrients entering the bloodstream. So blue is what goes into the stomach, red is what goes into the bloodstream. And this also is meant to mimic the toilet. Blue is the desired water level. So the water level was 0 after the flush, and then I immediately want it back up to 15 because all that water was initially used to flush the bowl, and then I want it to load back up into the tank, but it can't happen instantaneously. So you're modeling the sluggishness of the valve with that red curve there. Now this, in system dynamics, this idea of having this curve that jumps to a point, and then you watch how another curve follows behind it, this is what we refer to as a step response. So when you need to measure smoothing delays in the real world, you look for data where someone has actually tried, like in the toilet case, to generate a desired change that is a square like this, that is a sharp change. So you go from having 0 in the water, or 0 in the tank, to then needing 15 in the tank. And then if you can measure how quickly the toilet responds from this step response, you can then make an inference about what this delay parameter should be. And we've already talked about this. It's that magical time constant, which is this 63.2% level. So basically you go up to, you say, you know what the final level is. You then go down and say, what's 63.2% of the final level? At what time did the response reach that 63.2% level? And in this case, it was 2.5 seconds after the step. So notice the time is at 3.5, but the step happened at 1. So there's a 2.5 second time difference between them. And that allows us to then figure out what delay parameter we should then go into Vensim and put in. So that's what's going on right here. Okay. So this again is the time constant that I've talked about here. All right, so this is what I'm going to, so here's another attendance exercise that gives you an opportunity to practice that. And so the question here is, what is the appropriate time constant or delay parameter used that would be used for this example on slide 60. And so you can see here that I get a step at time 1. So remember that, the time 1 is important. And you can see that I get a response that is a smoothed out version of the initial input. So remember, we've got a magic threshold. Remember that the initial step happened at 1. So with those two things together, you should be able to calculate out a delay. All right, so things are running, we're at the normal regulation time here, but, and we've covered how to handle these things inside Vensim. The last thing that I want to cover here is how to handle these things inside Insight Maker. And I also want to cover the things, just point out a few advanced topics. This will only take a couple more minutes, but at this point, we've covered everything you need to know in Vensim to do the rest of the assignment. So if you wanted to stop now, you could, but I encourage you to keep watching. But that will have been the last attendance question for this. So the rest of this is kind of like bonus material. All right, so moving forward here. So how do we do this inside Insight Maker? And so it's just the same sort of thing. If you were to draw a variable that you wanted to implement a smoothing delay inside, you don't have to do a complicated stock and flow. What you can do is you go into Vensim's historical functions, and they have a smooth, just like Vensim has a smooth, and it has a similar syntax where it's just the thing that you want to use as your input, the time constant that you want for this smoothing delay, and then this initial value. And the initial value is optional, and it again matches the initial value of the input if it's omitted. Oftentimes you want this to be explicit, and maybe you want to just make it 0 to say that the initial value of this delayed thing is just equal to 0. But otherwise, this just works just like the thing in Vensim. So that delay is basically your time constant for the system. So we can do the exact same thing that we did in Vensim, where we can generate a step response, like with a pulse, and we can watch what the delay does, and it automatically is all implemented inside a single variable. All right. So again, if you have any questions about that, you can feel free to ask them there. All right, now I just want to cover a couple of, the last couple of slides here, just point out a couple of more advanced topics here. So I've mentioned step responses. They're super important to system dynamics modeling, and there are functions in Vensim and Insight Maker that generate steps. Instead of pulses, they generate just a step at a particular time. And this, in both Vensim and Insight Maker, they have a very similar syntax, but unfortunately the position of the arguments changes. And so in Vensim, if you wanted to generate a signal that at a particular time jumps to a particular height, then you go into that variable that you want to be the signal that makes that step change, and then you just implement step. You just put this function step, and then the first argument is how high you want the step to be, and the second argument is when you want that step to happen. So this is something you might want to do if at a particular time in your simulation you want to simulate a perturbation to the system. So at 3 years into the simulation, you suddenly get a massive increase in crime. And this is how you could implement that massive increase in crime. You have some crime parameter that then jumps up from 0 to 50 or something like that at that particular time. You can do the same thing in Insight Maker, but you put the time of the step first and the height second. So by doing that, then then you can see here that you can generate curves like this one here, where you have the step that, if I do step 1, 1 in both of these, because it's the same number, Insight Maker and Vensim, then at time 1, you get a curve that jumps up to 1 and it stays there forever. Now, we've talked about smooth as one way to implement these smoothing delays. Now, there are so-called higher order smoothing delays that create a sluggish effect that nevertheless changes somehow more quickly. And so those are implemented in Vensim and in Insight Maker. There's something similar to this with this smooth and then smooth 3. I'll start with that. This is a so-called third order smoothing delay, which is basically smooth 3, which has the same syntax as smooth, is like putting 3 smooths together, where each delay of the smooth is a third of the previous smooth, is a third of the total delay. So all the delays add up. Now, why would you want to do this? What this effect does is it makes it so that the initial output has a much slower rise than a single smooth. But once it gets going, then it actually rises much faster later. So this provides you kind of a way to move between a smoothing delay and a fixed delay. So a fixed delay, we know this green curve, if that was our input, the fixed delay would just be a curve out here that would be like a square wave that would jump straight up after a fixed amount of time. Well, this red curve, I hope you can see, is kind of in between the two of them, where it sort of doesn't immediately change, but then at some point later, it starts rising very rapidly. If you increase the so-called order of the delay, so in this case, there's this thing called a smooth in, you can then get closer and closer to approximating a fixed delay with a smoothing delay. And so smooth in, it takes the same first argument as smooth. It takes the same second argument as smooth, but then it it has a parameter here which allows you to change how many of these little smooths are kind of chained together. And the larger you make this number, this 20, then the steeper this curve is going to be, and the longer the period here where it's flat is going to be. So again, the higher you make this n number here, then the more your smoothing delay turns into a fixed delay. Okay. All right, so there are related functions here that you'll notice. So smooth and delay 1, these, for all intents and purposes, are going to be identical functions, but you'll see both of them in Vensim. Smooth 3 and delay 3, same thing, smooth in and delay in. All of these things, for all intents and purposes, act identically, but there are more advanced modeling challenges that you can do where they start acting differently. So once you can actually make things so your delay changes over time. So like a conveyor belt delays things constantly, but you could imagine the conveyor belt speeds up and slows down. When the delay itself is a variable that's changing over time, then these functions start behaving differently. But if you don't have delays that are changing over time, if you can't find smooth in your list, you can use delay 1. If you can't find delay in, you can use smooth in, and they're identical. So that's the reason why when you're looking down through these lists, it will look like there's duplicate sets of delay functions, some called smooth and some called delay. Okay. All right, and that's basically all that I've got to cover here. So, so that's what we've, if you have any other questions, again, feel free to put them into the questions link here. The only other thing that I want to bring up are the announcements, and this is just a reminder that by lecture E4, which is a week from Tuesday, a week from today, so it's going to be next week, then make sure you've read chapter 6 of Moorcroft. So we're skipping over chapters 4 and 5, although these are very useful chapters to read if you want extra review material. So this is especially 4 is very useful for thinking about delays. And of course, there's reading exercises and assessments and the perusal that you'll have to do with that. There's going to be a Muddiest Point due on Sunday, and the final project team proposal is also due on Sunday. So get together with your teams and write up this roughly 1-page outline which tells me what you're going to study, what is the major problem that you're trying to solve with that, what do you think are the dynamic variables that are important, and what are some of the causal links between those dynamic variables depicted as a causal loop diagram. No stock and flow diagrams are needed, but I just need to sort of see that you're starting to think more quantitatively about this system. Assignment E2 has been available, but now you have enough knowledge to do all of it. So the first question comes from lecture E1, and the second question in the bonus comes from this one. And that is due the Sunday after lecture E5. So you've actually got a lot of time to do that. So this is lecture E2. Lecture E3 will be on Thursday. E4 will be Tuesday. And then E5 will be next Thursday. So you basically have this week and next week to finish up assignment E2. Okay. So that again is all I've got for you. So if you have any other questions, feel free to get in touch. And thanks for hanging out this long for those of you who hung out for this extra 10 minutes. See you on Thursday.